that and then
Is there a way to like make this?
to make it a whole present?
Yeah, it's okay.
Yeah. No, so yeah, this. Over here, she can make it big.
Okay.
Cool. So you can push on there or the arrow keys, I think. Or, I don't know, my kids are hoping for a huge snowstorm to get them that.
How much are we expected to get?
It's variable. So the news said there's a high confidence of snow, but there's a low confidence about what the amount is going to be.
Yeah.
This morning I was hearing some places can see 6 inches to a foot.
Oh gosh. I have like my school placements on Tuesday and Thursday morning,
Yeah.
so I like signed up for the
Me
like
too.
notifications, yeah.
Yeah.
And like hopefully there's
But it's the northern areas and the ski places can get 16 inches.
Oh.
And then southern Vermont to New Hampshire might get 1 inch.
Yeah, so that's what we're calling. A lot of costly, or New Hampshire costly disappointed, so.
Well,
It gets it.
we have had a lot of our initial student presentations earlier in the semester, but given the class size, we do a lot of flexibility, and so it's Annie's turn to do hers, and I think Maura has one to go, and that will be everybody doing one of these presentations. I think a good warm-up for the final presentations in a way, so go ahead.
So I looked at, from my last homework, the homework problem 13.19, which is the nature nurture problem. And so just some background information on it. It was a 1898 study investigated the 1898 study investigated the effect of hereditary and environment on intelligence. So from adoption registers in France, researchers selected samples of adopted children whose biological parents and adopted parents came from either the very highest or the very lowest socioeconomic status categories. So they looked at 4 different categories. So there was the high adopted SES and the high biological SES, the high adopted SES and low biological SES, the low adopted SES and high biological SES, and the low SES for both sets of parents. And so they had 38 selected children who were given intelligence quotient tests. So the first thing that, and then this was the tables of how they were split up. So the adopted, biological, and then the 2 together. So it's 38 total. So the first thing that I looked at was the box plot of the mean scores, and so it's adoptive to biological. So the adoptive is on the bottom and the biological is on the top. And the first thing that I noticed was that the 2 on the outside, like they're both very high and both very low, is kind of like what we would expect. But then the 2 in the middle, like you can see that the variability is similar, and so it doesn't really have, like, they're so close that there isn't really a huge interaction, because if you were to switch the 2, you can see how like similar they were. So then I looked at the interaction spots, which you can also see are very similar. And because they're so parallel, they're parallel, you can see that there's like very low interaction between the 2 variables as well. And so then I ran the ANOVA for the interaction, and you can see that the p-value was so high. And so that just kind of like goes again, it's above the 0.05, so we can kind of like reject that initial null. And then I just found it interesting that the p-values for the individuals were lower, but then together like there wasn't that huge interaction. So like you can see that the variability of the test scores could be attributed to like the 2 of these, but then on a whole it's more like the SES in general has like a higher impact. And that's what I looked at. And I know that you had said
Yeah, we didn't get all that time to communicate before, but you know, what possibility if we look at residuals?
Mm-hmm.
You know, was there outliers or things like that, or any evidence of any need of transforming that IQ
Yeah.
variable?
Mhm. I thought that this like was interesting too to look at and how it differed. Maybe like it was in France, but in the U.S. as well.
And something about R squared,
Mhm.
right? So if you add up the sum of squares column, you get total sum of squares.
Mhm.
And then if you add up the sum of squares for adoptive biological, what percent of the variability would seem to be from those
Mhm.
things? So if it's about 1,500 and about 25, we kind of do that in our head. So it's like 3,600, and then there's another. The residuals are 5,900. So is it about a third, 30%, something like that? So it's not a huge determination of the IQ. It's not like an R square. It wouldn't be an R squared of 90% or anything like that. But still see like 25, 30%. Do you see where I'm kind of adding up the sum of squares and figuring out what percent would be the adoptive plus biological?
Mhm.
Yeah, 25, 30%, kind of an interesting split. So, but any questions about, a few of you looked at this one, anything else you recall being interesting about this one? Yeah, so no apparent interaction. So I've seen other social science research or psychology research done this way, where they choose the extremes.
Mhm.
Right, they kind of evaluate something and then choose the extremes, and then follow those up and see if there's a difference. And then kind of what would be the other way of doing it, like taking some from every SES and seeing if there's more kind of a gradual thing. So for funding and sample size and resources and things, take so many, if there's going to be a big difference, kind of think it's going to be at the extremes. But you might like some points in the middle. If they had 5 levels, maybe you'd like some, maybe half the sample size of the other group, but put it in the middle so that you might see kind of something in the middle.
Yeah.
Is it linear? Is it a jump? Or
Mhm.
something like that. So.
Yeah.
Good. All right. Thank you. Okay. Laura would have the last of those. So what we're planning to do is look at repeated measures. So we've been looking at time series. So 11. So chapter 16 is listed as repeated measures and other multivariate things. Repeated measures. And generally multivariate analyses. Right? And so the type of data that's covered like this is kind of like ANOVA, in that there'll be treatments and factors and things that we want to take into account. But it's kind of like time series, because we have multiple measurements on one subject or one unit, and those can be correlated. So it's kind of I think it's after these two, because we've seen some things about the impact of correlation over time, and we've seen some things about ANOVA. So this one kind of mixes in a number of things. So repeated measures and multivariate, in my mind, is not always the same thing. Often I think about repeated measures as you measure the same concept with the same variable, right, on a subject or a unit. Multiple times. And so this can have a time dimension. So where you measure the same thing on units over time. So this could be growth curves. How is one child growing over time, and what's their trajectory look like? If at the at birth and at 2 weeks and 12 weeks they're in the 95th percentile for height and weight, what are they at age 2 or age 4? Do they stay in that trajectory? How do things level off as organisms reach adult full growth stage? Right? These things could be do this. So still measuring size or different aspects of size over time, or the IQ, education examples, how is development happening? And from year to year, do children move up at a full grade level equivalent in terms of learning? So there's a possible time dimension. So growth curves, sometimes these are called longitudinal. So it's measuring over time period. There are various surveys that are longitudinal surveys. One of the biggest one big important one is the current population survey that measures unemployment in the United States. So the size of the labor force, amount of unemployment, employment for the country and for larger states, maybe even a couple metro areas comes out of this survey. In the current population survey, a household is selected and it's interviewed monthly, right? And it's interviewed for 4 months. Are the adults in this household, are they employed for regular pay? Is it hourly work? Is it salary work? What's the amount of pay that they're getting? Number of hours? What benefits they get and all that? So they interviewed for 4 months, right? Because there's a correlation over time. And then the house takes a break and is not in there for 8 months. Right? And then they go back to that same house again and measure them 4 more months. So it's a longitudinal with this kind of interesting structure. So the 4 to 4, they're getting month to month or quarter to quarter variation. And then this one, the early months to the late months, is getting yearly variation. Is unemployment changing on a yearly thing? So it's a combination between measuring things at the current time period and then changed other time periods. Right? The National Resources Inventory is another very large-scale national survey of environment where over the course of many, many years, they survey all the land area in the United States and see what it's being used for, what's growing there, and measure things like erosion or water quality on those things. And there's a big rotation scheme where different areas and counties would be revisited once every 10 years, once every 4 years, once every 12 years, once every 18 years. So it's just a massive longitudinal survey, right, that's going on. But sometimes repeated measures just don't have a time dimension. You go into a doctor's office and you're doing a medical study and you measure blood pressure once. Well, blood pressure is variable, right? And it's affected between the first and the, some people have more of a reaction to being involved with a kind of a white coat syndrome. They're being backed by a doctor, so their responses are a little bit different. So sometimes people measure them twice, right? Kind of, or maybe 3 times. And that's a little bit of a time dimension, but more is for the purposes of just averaging to get more stable measurements. So anyway, sometimes simply take multiple measurements. Right, to reduce variability. So sometimes that's done. There's multivariate analysis is there's kind of an interest in multiple outcomes. Y1, Y2, Y3. You're interested in 3 different aspects of things. So when you're measuring children, like the IQ example, maybe there's a math IQ, there's a reading IQ, and there's other aspects of testing that you might have. So every child might have multiple outcomes that you're studying, and those are correlated with one another, right? There's some children, there's kind of this latent trait of intelligence, just general test-taking ability and knowledge, maturity, and it affects all of them, right? So they're correlated. So you might not analyze them all separately, but put them together and do some joint analysis. So multivariate covers that, and the repeated measures is more this, I think of it more as the same thing being measured over time, but sometimes they get mixed, right? You could have 3 elements of education achievement measured over time and interested in how those are playing out. So it's a diverse area looking at this. Some fields you would take a course in repeated measures, longitudinal data analysis. Environment, medical, economic would be extremely important. And then you also sometimes take things in multivariate. Multivariate, increasingly kind of modern multivariate, has more graphical components to it. Classical multivariate is looking at matrices and projections in subspaces, kind of principal components, analysis and all that. So it's a big diverse subject, and we're going to talk about a little bit of it. And to me, getting into things as models get more complex, as the data structure gets more complex. There's more choices about what to do and more approaches. And I think it's critical from my experience in dealing with these is to understand what the data are, what actually was measured, and try to get back to the most simple, basic measurement that you can get. Often people process data where they take averages of multiple measurements, they take summaries of multiple measurements, and in that summary information, sometimes you'll lose information, right? So to do that today, to kind of explore that, I want to talk about one of the case studies, right? And initially I found this very confusing about what was being measured and how they were doing it and what a couple of the graphs in the book meant. So I don't know if you've looked at this one. I didn't forecast too much that we would be coming into this section, so maybe you haven't. So let me introduce the case study and then talk about how we might analyze it. And just in comparison to what the book does, my inclination would be to do it a different way. They're both, I think, valid and probably get some of the same conclusions, but I think there's a way, I don't know. Anyway, to me it struck that I would probably approach it different. So in this study, monkeys are being taught different words or to recognize different objects, right? Like telephone, right, or phone, right? And so then the monkey's supposed to point to, 2 pictures. One of them is a phone, or one of the objects is a phone. Based on the word, can the monkey identify that? And apparently they're very good at this for many objects up to a certain point and certain complexity, that they can do it. And they are taught 20, I'll just say words, but I think there's some objects or pictures at 5 time periods. So there's 100 words in all. Right? And they are 16, 12, 8, 4, and 2 weeks before the treatment. Right? And so presumably when they're learning it at 16 weeks, 4 months before the treatment, they learn the words and things like that and are successful in understanding these things. And at 12 months, they learn the 20 there and so on. We don't have a measure of their performance when they're learning, but I presume it's very, very high, or they keep training them until they know what's going on. Yeah.
Did you say what the treatment was?
No, we haven't said what the treatment is. So this is an experiment that I don't think they would do anymore, right? And so the experiment is to block part of the functioning of the hippocampus in the brain. right, for some of them, right? Some of them are not, they don't block it because this is an experiment on memory, right? And what does the role of the hippocampus play in memory recall? Is it involved in short-term or long-term memory? Some people that receive brain damage from either strokes or accidents or military operations, right? And get parts of their brain damaged, they want to know how can they recover, right? And what type of treatment they could do. So there's a rationale for doing it, but I don't think we would treat monkeys like this or other primates like that anymore. But you know, it had it's certainly its rationale because there would be human populations that would be affected, and so the question is, so treatment, right? There were 18 monkeys in all. They randomized into the treatment, which is block part of the hippocampus. Right? And then control, right? Just unaffected. They don't do anything to them. All right. And then after treatment, right, test the monkeys on the 100 words. And so they're going to see, do the ones with treatment versus the ones with control get better recall of these different things. And part of the scientific hypothesis is some of these are done at a later, earlier, right, time period, earlier before the treatment, so that they're further term in their memory, right? And these are kind of a couple later time periods, more recent effects, right? And so things are reduced to early versus late in the analysis. But of course, one thing that you can quickly see is if you don't reduce it to early, late, but actually have the number of weeks, is you have some graphs and things, and numerical summaries are presented by the number of weeks. But making a choice here is an experimental choice, early versus late. And if the only thing that's published is the early versus late, you've lost a little bit of information that might be useful in there, right? Right. And so this is, they reduce it to the percent correct in the early and the percent correct by late. And so they call this repeated measures because each monkey then has two scores, an early and a late score. And they're correlated, and you want to see if there's a difference, right? But I think the thing, then they do multivariate techniques because you have two outcomes. Say, is there any effect? They use something called Hotelling's t-squared, which is like a generalization of the t statistic for testing. Is there any difference? But I would approach this type of situation. Let's think about models that we might, use for the data, and what data do we actually have? Right. What do the data in its most basic form, in its most fine-grained, detailed form, really amount to? And so we have 18 monkeys. Each monkey is going to get 100 scores from evaluating those. So there's 18 times 100, 1,800, not 1,000. Right, 1,800 different scores. And so let's call those scores Y, I, J. I going from 1 right up to 18 for the monkeys. Right, and J going from 1 up to 100 for the words or objects that they're trying to recognize, the kind of comparisons they're trying to get. Right. And so ultimately it's those yes-no scores that are really the data. The procedure they use is to aggregate that, the score for each monkey at each time period and so on. So they reduce it so you don't have quite as much information. So when it's like this, you know which monkey got which score right or wrong, right? Which could be useful. Right? So a basic thing they want to know is treatment, right? So getting down, we can have a variable t sub I. It's 1 if the monkey's in the treatment group, and 0 if in control. Right? A very simple model would say there's an intercept and then some effect of treatment, and then some error. Right? We might want to run a regression that says that, well, these are 0, 1, so I'm not going to try and make a little graph. That's another complication that comes out of this. And if beta 1 is for treatment, if our coefficient beta 1 then would be less than 0, then treatment by interrupting the hippocampus, I don't know if that's surgery or just temporary drugs or some other thing, right? Then the treatment, if beta 1 is less than 0, then treatment hurts memory recall. So that would be a very basic thing, right, to start with, right? Model. But right, some words are early and some are late. There might be a difference between recall versus early to late. That's a scientific hypothesis, right? So we need a new variable, right? Some of these words are early and some of them are late according to that. So to build up from that model, we can introduce a new variable, and that has to do with the words. You know, j equals 1 up to 100, you know, words or objects. So this thing can be 1 if it's an early, you know, time equals 16, 12, or 8. And then it's going to be equal to 0 if it's was introduced to the monkey later, closer to the time. So it's more of a short-term memory thing to recall that. Right? So now we could do a model that has the treatment effect along with this early and late, and put an interaction in there. Right? So an expanded model, Yij, could have beta 0 plus beta 1 time plus beta 2 times early and late. Plus we could have an interaction, right? It takes the time indicator times this indicator with some error over here. And then this interaction would say whether there's you know, in terms of getting your score, right? Is there an interaction between those two, right? So some of the scientific hypotheses here would say, so if this is a treatment, well, the pictures they have in the book are ones like this, where there's early ones, so, and then later ones. And what does the picture show is that the two kind of predictions are kind of similar at the ones that are more recent, right? Short-term memory. But the early ones have something kind of like this, where this is control and this is treatment. There's only really 4 lines because each of these are binary, right? You add beta 1 or subtract beta 1, you know, it goes down if it's treatment, and then there's early and there's this interaction. And then both of them are kind of similar here, right? Treatment, control, and then both. So it looks like from the hypothesis that the hippocampus is involved in the longer term, maybe I have to get these backwards, right? But it's more involved in the longer term memory rather than the short term memory, right? So that it does seem to hold up, that it does that. So if somebody had a stroke that damaged part of their brain, or they were in an accident, or military were injured, and that part of the brain was damaged, then the treatment should pay attention to what type of memory loss they might have, right? Right, so you can do that, but there are multiple measurements on each monkey in the different time periods. So the way that this model could fail to really represent things is the epsilon i's might not be independent of each other, right? Due to repeated measures, the ICJ is not independent. And we've seen how much of an impact in time series the non-independence can make. Like, it can easily double standard errors and cause other issues. Why wouldn't they be independent? Well, each monkey's measured over time. Some monkeys could be just more able to do this, right? Smarter, more attuned to this activity, and so they could just get higher scores. Right? So they're going to have positive residuals because their scores are going to be higher than predicted. And then others just don't do it as well. So they're going to get negative residuals, right? All correlated. You might get some monkeys that get into this, right? They start out not understanding what's going on, but then, oh, it clicks. And then they take off, so they have negative residuals that could become positive, so they have a pattern. And there could be other shifts, right? Some monkeys have been there longer, some have interacted with probably their trainers more. Maybe they make a certain bond, or a bond gets broken, and so things suddenly kind of shift, right? So you can have these things that are not independent because you're doing repeated measures on the subjects, right? So many reasons there. One way to deal with these things is the correlation is a random effect. For each monkey. Right. The reason to have a random effect in there for each monkey is to capture, right, some correlation and individual specific effects. And so the way that this gets specified, one way is just to have an intercept effect for each monkey. So instead of having just one beta 0, we could have a beta 0 for a particular monkey that is a beta 0 plus some effect here. Right. The effect for monkey I. So that would just move some up or move some down, kind of a very basic shift for individual monkeys. And we're going to put a distributional assumption on those, that they're normal with some error. So we have our 17 monkeys. It's kind of randomly drawn from some population of similar individuals, and these 17 then are kind of a random sample from there, right? So the model, as we add that, in that is going to be expanded. So the Yij, I'll write it with an intercept and then this alpha I here. And these things are given a normal distribution. And then we can have our beta 1 for treatment and our beta 2 for early versus late, and our main effect or our interaction effect plus an e sub ij. Right? And these things, they don't have a normal error terms, and I'll put a little sigma squared epsilon on there. The assumption is usually made that these are independent of each other. The alpha i's are independent of each other. Then these errors are assumed to be independent of each other. And further, the covariance between the alpha i's and the alpha ij's is 0. Sometimes it would be said that those are independent of one another, with the normality assumptions covariance, meaning same as an independence, right? So there's a lot of kind of assumptions that goes into these models, right? Can we really test these assumptions? Not so much, right? It's pretty challenging to evaluate these different things, whether these are there, right? So what does this model end up kind of implying, right? It implies something about the relationship between measurements, right? So we could have, what if we take two of our measurements on one of the monkeys. Right? So we have y sub I j and y sub I j prime. If they are both in the monkeys are treated, right? If both questions are early and or both of them are late, they have the same average. But if one's early and one's late, then you get a difference of either beta 2 or beta 2 plus beta 3 in terms of the average difference, whether it was a treated monkey or not. But the correlation implication of this thing, right, is what's the covariance between these two measurements. Well, the things that impact covariance, what treatment its group is not random, that's assigned by the monkey, is the word early or late in the sequence, that's assigned. And so it's really these two parts, these two random things here that determine variability, conditional on the other things. So it's really the covariance of this alpha terms times epsilon ij, and then for the same monkey, you have another alpha I plus epsilon I j prime. Right? And the epsilons and the alphas are independent, and the different epsilons, see, even though that's an I and a j, that's an I and j, those are different random terms, so those are independent. But the alpha I in itself, that's the variance then of alpha I, which is sigma squared alpha. Right? So the random effect in there induces a covariance, hence a correlation, among measurements on the same monkey. The variance of just a single measurement, well, the things that contribute to variance are, again, the alpha I plus the alpha ij term. The other things are considered fixed, the t's and the e's. And so if these are independent, you get to add the variances together. The variance of this alpha ij, and that's a sigma squared alpha plus a sigma squared epsilon. And kind of add the two variances. So the correlation, and that's going to be the same for both measurements. And so the correlation is this one over that one. It's called the intra-cluster correlation that we used that term before. So the correlation between yij and yij prime, a different question, for the same monkey is going to sigma squared alpha over these things. Right. And that's kind of referred to as the intra-cluster correlation. Right. So now you induce that these things are not in, yeah.
So just to clarify, for this situation, the main benefit of finding the covariance is to use it for our correlation here at J-cluster?
Right, so because these are measurements over time, the errors might not be independent, and one way to induce this correlation over time in the model is to put this random effect in there.
And just, like, in general, like, what is the covariance itself kind of tell us? Does it tell us much, or?
So covariance, I mean, it's going to be either positive or negative. If it's 0, then they're uncorrelated, no covariance. So the magnitude is always, it's scaled by what the scale of the y variables are. These, the other wrinkle with this is these are really 0, 1 variables, so we might not really want to be using a linear model to predict this anyway. We will get into logistic regression, is what you really would use to predict 0, 1 variables. the book in their analysis avoids that problem, 0, 1, because it takes percentages. You know, its scores are all 95%, 90%, 90, 85, and so on. So it all has scores that then it can try to predict. Right. But in principle, it does induce this covariance. And you know, you can convert it to correlation to kind of see things on a negative 1-to-1 standardized scale. Right? So I would think about doing that type of analysis and using a model that has, you know, the main effects we want, but something, and keeping the measurements at 0 and 1. Right? Now I think there's some big advantages. So in R, you know, how are these things done in R? Well, if you had a linear model command that said y could be as a function of our treatment plus our early versus late, and a multiplication of that, you know, given our data. That's the linear model. There's an LME4 package for fitting linear mixed effects models. And linear mixed effects regression, you specify things much the same, but you add notation for a random effect. This is the number 1 here, given monkey. Right. And this LMER command will add that random effect term in there. You could put monkey as an effect in there, but that's going to give you 16 extra or 17 extra coefficients because there's 18 monkeys. This one just has to estimate that one sigma variance parameter. But anyway, we can look at some. I didn't get that printed out just before class, but I have some code that we'll look at doing this. Right. So thinking about writing the data, converting it not to the percent that each monkey gets right at each time period, right? Because then each monkey would get, or the percent that they get early or late. But by going back to the YIJ, the original 1, 0 variables, and which question it was and what time period, and keeping that detail, I think there's at least 5 extensions that you could do to this model, right? So our model that we're working at has a time effect, a treatment effect, an early versus late effect, and that interaction. But there's a number of possible extensions to the model. That I think can be worked in to this linear models framework. Some of them could be done with linear models, but some of them are kind of special to keeping the 0, 1 variables, right? One general one, right? Is there anything else you'd like to add to this or change the model in any way to get a little better information? What's in our model now? Go back up. Back to this one. We have treatment and early versus late, and then the interaction. Any enhancement you would like? Yeah.
Maybe the difficulty of the word.
Yeah, so difference, you could have something about the characteristics of the words, right? If you summarize your data as % correct, how can you include anything about the words in there, right? But if you have the words, every score for every single word, you could group them. Are they about familiar things like fruit and things in the environment? Are they about different things like bicycle wheel or an elephant? Something that might be different than their normal experience, right? So you might classify words somehow, right? So you can. So definitely, there's a couple of things. I'm going to put this as a third one, that these ones are kind of special to keeping all the detail. You could have characteristics of words. Right? Familiar ones, less familiar ones, if you could classify them somehow, right? There's another class of models used in psychology and other measurement issues, item response theory, right? you can estimate item difficulties. That's going to be beyond what we're going to do, but to do that, you would need to have the results for each word. Right? If you classify the words a little more simply, is it, maybe some of them are visual, and maybe some are oral, or maybe physical objects. So if you had different ways of presenting information, you could see which one do they do. So yep, that would be one thing you could introduce if you had the raw data. How about that early versus late? You have 5 time periods, right? So you could, 16, 12, 8, 4, and 2 were the different time periods. So you could use that instead of simply early introduction versus late introduction. And that's not really so special to keeping the data. If you kept it by time period rather than group it as early versus late, you could do that modeling too, right, in there. So the linear model could handle that one. How about these monkeys, right? What aspect of the monkeys themselves could affect their learning or their
Age or maturity.
Yeah, you could have something like age, right? You could put gender in there. Maybe there's some difference in long-term versus short-term memory, or something different about part of the functioning of the brain. Once you start messing around there, it has deeper things that we don't understand, right? So age, gender, but you said maturity as well, right? Some of these monkeys might have been in this environment for a few more years with the same trainers for a few more years. And then to do this, they might be, gathering, subjects, individuals from different environments to kind of do a bigger study, right? They might not all be at one zoo or research facility. They might be at different places. Right? So that might be something beyond just age, so experience. Right? Again, the linear model probably can do those two, or the mixed effects model could incorporate those things. Maybe I'll call this number 4, because this is kind of really special to that. There's characteristics of the evaluators, right? Because this is an interactive thing, right? That they show, I don't know if they do it on a computer screen or they have to touch a button or something to pick out something, if that works out, or there's a person sitting there, right? So if they have a favorite trainer or a person who cares for them that's doing the research, if some of them have that connection but some of them don't, or different people are doing it at different times, if you have the raw data, you could put that into the model as an effect, right? So maybe, we studied some of those data sets on the Pygmalion effect. If kind of the monkeys are intelligent, maybe they sense a little bit about what is going on based on how it's presented. It's kind of a subtle thing, right? So in a lot of survey research, there's a real concern about the respondent-interviewer interaction. Do people respond the same way to questions depending, if different people are interviewing them, or it's done a different way, over the phone, in person, and so on. But keeping the detailed data allows you to go back and try to examine some of those hypotheses, right? So characteristics of words, you need the detail. Something else is you could have random slopes by monkey, right? So it gets to be a lot of variables if you try to, a lot of parameters, if you try to give a separate effects for each monkey at each time period, or early versus late. That's just a lot, right? But like we would do a separate intercept, you can have random effects like a random slope. So what's the impact of early versus late could could vary not only by treatment, but by monkey. And an efficient way to parameterize that is to have another random effect in there. That not only the slope, but the effect is there. You probably would not have random slope for early versus late effect here. You wouldn't really have a random slope for treatment because the entire monkey the entire time is in treatment or not. It's not something that they go in and out of, right? So anyway, you could do something like that, right? So there's many ways you could enhance this model if you have the data and can think of it beyond that. The other last thing I'll mention is that when you go back to this original data, it's really 1 or 0, predicting 0, 1 variables. It would be preferable to use just the regression. Regression, which is really kind of chapter 2021 coming up. We will talk about it. It's kind of a little bit late in the course, but if you wanted to do look at that as a project, it would be something that would be possible. So if you have data that are success failure, it's very similar to regression modeling in terms of specifying the model. There's a slightly different command for generalized linear models to make it work out. So I'll describe what the textbook does, and then maybe we can see if we have a little time to set up. We might not have time to set up the data. Right? So the textbook lists out the 18 monkeys they have, the week number that where they were 2, 4, 6, or no, it was 8, 12, and 16, and they record the percent correct, right, of these. Right. Each of these is based on 20 questions for all those, right? There's these ones have, say, treatment or control, they list at the top. There's 7 of those, and then there's 11 individuals that get treatment. Right? So there's that division. They also summarize this where they get the 18 individuals, and then they do early, and this is based on 60 questions, and then the later introductions are these 2 and 4. These 2 are late. Those are based on 40 questions, so it's not really equal in there. And so they reduce all of this to a bivariate outcome. Right? So they have yi1 and yi2, 2 scores. And then the methods they implement are is there an average difference here, treatment control? Is there an average difference here, treatment control? And they do a test to say, is there any difference between either of these 2 variables across the different groups? And so that's where they get the multivariate thing. But I think that the analysis kind of obscures some of the elemental data that you might have. So this type of issue I experienced at George Washington University in speech and hearing. Did some consulting work, collaborative work really. I mean, it wasn't paid or anything, but it was collaborative work with people there. And the issue here was what do children with cochlear ear implants and in total or partial deafness hear? And can they make sounds? Right? And so when the researchers initially came to me, they had summarized scores. There were children with cochlear ear implants. They get them very early in age, maybe even before 1 year old, or certainly not much after. The children are deaf in 1 or 2 ears, or partially deaf. And then to augment what they hear, they get this implant that takes the sound wave into the hearing center of the brain in the ear, and then they get the vibration and interpret it as sound, versus comparable children with normal hearing, just to have normal hearing ability, right? So you have 2 groups, and they're going to evaluate them at different time periods, right? They're going to have them come into the lab at this time period and 6 months later, and so on. And at the lab, they have them try and recognize, kind of very much the same setting, these are 2, 3, 5-year-old kids, different sounds. And they don't have them write them out, or they just have them kind of point at things because they're such young children. And the data were summarized as percent correct. I mean, exactly the same way. But underlying this was the correct or things on different questions. And some questions then were repeated for different children. So, in addition to saying, what's their average score, are there certain sounds that are harder versus others? And you need the very fine level data to look at that. In some of these things, there's also a time effect, right? Children get bored doing these things in a lab, or get distracted, and so they might go for a little while, and then their performance kind of drops off, right? And if you have the exact sequence of things over time, you can have a time effect, early versus late. In any case, so these type of data outside of that example really do come up. We'll look at numerical summaries for this next time, given the time. But I can at least show you what the book, I kind of started this, but I can get it a little bit better. That we can slew 3, oops. Why doesn't it want? It's library. Oh, it's not there now. Something's gone away. Let's see if I even have the data now. No, can I type that? Okay, 1601. Does it? No, it doesn't know. I'll have to do it next time. But anyway, to kind of show you, you can look at the book on that chapter, and the data are presented there. But it's a little bit of work to recreate the 0, 1 variables and make something kind of like that. Yeah.
Is our next homework going to be due next Monday or this?
I'm thinking next
Friday?
Monday, right?
Okay.
So we're picking up one now on the time series, and then we'll spend a couple days
Okay.
on this chapter. We're not going to get into all of the details, but kind of just look at one of these random effects models and have you do something for next week. We'll move on to categorical data on Friday, but just have some time to do it. So, anyway, all right. Go ahead and stop there. You have this homework.
No, I'm so sad. Me too.
Thank you.
Yeah. Thank you.
You're welcome.
Thanks, I think it works well, sending, drafts of things
Yeah.
before. I'm happy to do that. So,
Okay.
Yeah.
Yeah, I wasn't sure, but sometimes I have a hard time understanding the question. So the way I interpret it, I'm not always sure if that's how you.
Right, yeah.
want
What
us
kind
to
of
interpret it,
thinking
but-
you could do, and so,
Yeah.
Sometimes at times it's if I write the original questions, that I don't necessarily specify it as well, or sometimes the
Yeah.
book has a real short question, but in my mind I'm thinking, well, you probably want to look at this and that.
Yeah.
And so.
For the final project,
Yeah.
Is it individual or partners like the first one?
It can be partners.
Okay.
If it's partners in the write-up and the presentation, or it can be a little bit, longer.
Longer, yeah.
A little more involved, but
Okay.
so,
I just wanted to check because I
Yeah.
wasn't sure.
yeah, no, that's fine. Are you
Okay.
thinking about doing a joint?
I was
Project?
thinking Annie and I were thinking of working together.
Okay, good,
But we wanted to.
because you're
check
both
to see.
education.
Yeah.
Yeah, so good, so,
Thank you.
yep.